Okay, now we will consider subdivision. And also we will talk about sublinear expander. So now we can consider this parameter. So in other words, what average degree of graph G ensures that it contains a subdivision of KT, complete graph on T vertices. For lower bound, you can first consider, say, complete bipartite graph on K sub, say, T squared over 10, T squared over 10. Then what happens? If you have a copy of subdivision of KT here, then how does it look like? So it's like passes between these vertices. And you say that these vertices with the degree L3 are the branch vertices. If there is a copy of a subdivision of KT here, then there must be some branch vertices here. And we don't know how they are distributed, but at least half of them should be on one side. So at least T over 2 branch vertices should be here. That means there are some passes between each of them. And because this is an independent set that has to go through the other part, thus giving you at least one vertex here are participating in such path because they are vertex disjoint. That yields what? T over 2 to too many passes between here, and then each of them uses at least one vertex from here. But what's that? That's at least like T squared over 8 minus T over 8. That's strictly bigger than, assuming T is large, that's strictly bigger than T squared over 10. So there are not enough vertices here to accommodate all these passes. So this does not contain any KT subdivision. Okay, and this has what? Average degree T squared over 10. So it suggests that this is some constant times T squared. Indeed, this is the power of T squared. It's shown by Komrosh and Semoredi in 1996, independently by Bollovach and Thomason. Also, cross time, 1998. They confirmed that this is big O T squared. So in other words, if you have a graph with average degree, at least some constant times T squared, and you should be able to find a copy of KT in there. Self-proof uses different technique. So here they are using the concept of linkage. When some collection of points is given, you want to find the vertex disjoint passes between them. When can we do that? If you have a large connectivity, can you do it? So that kind of approach was taken here. And Komrosh and Semoredi uses something called sublinear expander to prove this. So we will talk about this concept, how they prove. So what is sublinear expander? Before that, what is expander? There are several types of graph which are called expander. And all of them are essentially you have certain vertex set and you consider its neighbor. Then that neighbor is not small. So in other words, you are here, so all the vertices, and then you move to your neighbor, then it scatters around, and then it occupies bigger space. So it kind of expands That's where the name comes from. Usually, I mean, you consider like edge expansion. Like for every vertex, let's say the number of edges between U and complement of U is at least alpha times some D times size of U, or vertex expansion. Means that you consider a vertex set and then consider its external neighborhood. And that is either list alpha times U for some positive number alpha. And usually you consider it as a more or less deregular, almost deregular. Either completely deregular or most of the vertices have a vertex, degree close to D. So those are the usual setup. And then they have many applications in many areas. For example, you can, in here, if you have this graph, you can consider like random walk. So you start from some point and then you move it to 1/4 probability to one of them, and then 1/3 probability to one of them. That's your random walk. And then you see how the distribution is converging to certain like stable limits. And yeah, so usually, it's expander means that it is back mixing. In short time, the distribution of your location converges to the, limit. So it's related to this expansion concept and random walk. And also this expansion is also related to the algebraic property of the graph. The eigenvalue, the spectrum of eigenvalue, that has also close relationship with this expansion. And also it's used for like error correcting code or coding theory in theoretical computer science and etc. It has lots of application. But one weak point of this is that this is quite strong property. So if you consider arbitrary graph, and usually the graph that we are consider could be, arbitrary, could be not really friendly to us. Then those graphs might not satisfy this kind of a strong property. So not all graphs satisfy this. So one of the attempts is that we can instead consider weaker property so that the more graph satisfy. So we consider weaker expansion property. That wider classes of graph satisfy. Based on that, Komrocki and Semoredi introduced the following concept of expander. Say epsilon is fixed and say K0 is fixed. Then let's say rho of x, which is actually depends on this parameter epsilon K0 as well. Let's say this is 0 if x is too small. And it's at least epsilon over log square 15x over K0 if x is bigger than K0 over 5. So these choices of dividing 5, multiplying 15 is not too important. those numbers are just out of for convenience, and then this is the originally how the Komrosian family wrote. So we follow this. So our graph G, we say that this is an epsilon K0 expander. If every subset X of guys say at least K0 over 2 and most the half of the number of vertices or satisfies that let's write this as the external neighborhood. But this with the vertices not in X. So in this section, let's write it this way. That has these in the there is this U in X, such that UB is in S. So let's say this is the external neighborhood. And this external neighborhood is at least rho of size of X times X. So what is it? So before here, the expansion ratio was constant. It's same for whatever set you take. However, it's different here. So this is the function that decrease as X increase. So if X is bigger, then their expansion ratio could be smaller. However, so this is roughly 1 over log square. And we know that X over log square X is increasing, while 1 over log square X is decreasing. So expansion ratio itself is decreasing. So for bigger set, the expansion ratio might be smaller, but the external neighborhood itself is bigger. Anyway, so this allows a weaker expansion. For smaller set, it might still have to expand in here, but for bigger set, it's expanding in much weaker ratio is fine. So sometimes this is called KAIST expander. There are also lots of other concepts of sublinear expander. So something like this. So we consider the, weaker expansion, and which are more or less similar but a bit different in some aspect. So to distinguish this from others, some people call it KAIST expander. K and X coming from Komrosian family. And okay, so we see that this is weaker. But why is it useful? It's useful because of the following two lemma. Let's say theorem and lemma. So one is the following. Let's say epsilon is small. One. Okay, that's not, I can actually write some number here. Okay, let's say, some number. Let's say this is small. The specific expression here is not important. I will just say this is more than like 10 to the negative 10 or something. And say K0 is at least 1. Then what we can show is that whatever graph we have, every graph G has an epsilon K0 expander as the subgraph H, which certify that its average degree is almost same with the average degree of G, and minimum degree of H is at least half times its average degree. So what does it say? Your graph might not be an expander in this sense, but it always contains a subgraph, which is an expander. Moreover, that subgraph has almost same average degree as U. So this is quite useful. So for such type of graph that for given average degree, can you find some substructure? For example, we want to know whether if your average degree at least like some constant times t squared, can you find the KT subdivision? There it's useful. You start from G, which might not have might not be a expander, but has high average degree. Then you find your subgraph H, which is an expander and then have almost same average degree. If you find the KT subdivision in H, then that's automatically KT subdivision in G. So you can assume this in this problem. So this is useful. And another reason why it's useful is that if you have a epsilon K0 expander, say G, and if you have a two vertex set, x1 and x2 of size and lift, say x, and another vertex set, W of size, say, and most 1/4 times rho x times x. Then what? There exists a path in G minus W, the path that does not pass through the vertices in W, and that connects x1 and x2, and the path has length at most 2 over epsilon times rho cube times 15n over k0. What it means is that between two large steps, you can find the path between them, avoiding some smaller steps. So why would it be useful? Roughly how we will find the KT subdivision. We take one vertex and then we find some path and then we find some path. And while finding some paths, we want to make sure that our new path does not intersect with the previous path. So for example, we want to connect this and this, but we don't want to get into the situation that this uses one of these vertex. And what we can do is we let everything else here to be W. And somehow, I mean, this is one vertex, but somehow you show that this is connected to this large set x1, and this is connected to large set x2, so that the W is much smaller than x1 and x2. And this lemma shows that there is a path here, which does not use any of the previous vertices. And you can keep to that until you find the subdivision of KT. And then next time you add this path to W, so this is your UW, this is your UW, and avoiding this W, you connect this to with some other vertex as well. Because this is short, you can control the number of vertices in W, because each path is short. Okay. So that's intuitively why this lemma is useful. And also the proof of this lemma is not difficult. what can you say? You have x1, you have x2, and then you have say w. And because this is sublinear expander, you take this neighborhood. Then that neighborhood has size at least rho x times x. But what do you know? If w is smaller than this, quarter times this. W x size at most quarter times this. That means some of them might be in W, but some of them are not in W. That's still at least like half times rho x x. Okay, and then now you take this and then you expand again and expand again. Then what happened? Every time this set now size y, this new part is at least size rho y and y, because this is bigger than rho x and x, because this rho times the IDX function is increasing. That means this is still bigger than 4 times w. So even you delete some parts which are in w, it's still expanding by this much. So each time it's actually expanding this way. If you do it r time, then what? So essentially this rho is like 1 over log square n-ish. I mean, it depends on f, but. And then how many times do you do that? You do, say, 1 over epsilon times log cube times this. And you can show that this is log square and then this is log cube. You will show that this is like at least e to the log, single log, which is linear in n, bigger than n over 2. You do the same thing here, then at some point, both sets have size at least n over 2, at least n over 2 on n vertex graph. So they must intersect at some point. That means there is a path. Moreover, the length is 2 times this. So that's basically proof of this. Yeah, I will not write down the proof in more detail. And also the first theorem, we can also prove this. Consider a function gamma. Gamma of x is like some 1000 times the integral of x, I mean u from x to infinity. And we take rho u over u du. So rho of u is like 1 over log square times u over 15u over k0. And this is essentially integral of 1 over u log square u du, and antiderivative of this is like 1 over log u. So this is roughly, we know that this is roughly 1 over log u. Some constant times like 1 over log u-ish. Technically, I mean, you can say like x. Yeah. So technically, so that's what you know. So keep that in mind. And what we know is that this gamma of x is like, so this function becomes 0 at u equal k0 over 5, right? So whatever you take, it's at most like k0 over 5 to n plus use this one, and then from your choice, epsilon is small, so you can actually take that this is at most 1 for any case. Okay, and why do we need this function? This function is like roughly 1 over log, and that has the that give us the following function on graph. Say for a graph G, we write pi of G is 1 plus the gamma on the number of vertices in G times the average degree of G. Okay, so what's average degree? Average degree is like number of edges 5 times the number of vertices. And here, because we are multiplying this essentially 1 plus 1 over log on the number of vertices, that this function will satisfy certain property. And we will see that what's interesting is for given G, we can take a subgraph H with a maximum pi value. So out of all subgraph, you compute the pi value. And you compute take the one with the largest value of this. So this is a bit of reminiscence of what we did for the previous, proof. You take a minor of them so that it satisfies this inequality. Then you get the minimum degree condition, and then the two adjacent vertices have lots of common neighbors. So their minimum degree condition was there because if you have a graph which satisfies the, smallest one with a certain average degree, at least something, then there, if you have one vertex with too small number of neighbors, then deleting it would benefit you. The density goes up. So it contradicts the minimality of that condition. So if you take the minimal one, then it must satisfy certain minimum degree condition. And here, this is roughly similar. You take the subgraph with highest average degree, then that's the most dense one. So if we forget this, then this alone already give you that if you have this H with the maximum average degree, then what? You still already have a minimum degree condition. If this has too little degree, then deleting it would increase the minimum degree. However, now you multiply this function, and then it's maximal in terms of that. That allows you to a bit further. So before, this deleting it increased the average degree, but now what we will see is that if in here, if this graph H has like low connectivity in a sense that here is big set, small set, big set, then you will see that either this one or this one will have a higher pi value if this is too small. You can kind of see that without this is kind of linear. So if you have this is n1 vertex and n2 vertex, and their sum is bigger than n. Yeah. And if they're disjoint, their sum is equal to the n. But now you multiply that, then what? 1 plus gamma n1 times n1, 1 plus gamma n2 times n2, and 1 plus gamma n times n. So these were like a linear function, but this is no longer linear. It's like slightly decreasing. It's so that you will see that this and this, even if its intersection is small, then this two term and this, if it might be bigger or equal. So you'll see. So I wanted to try to give you some intuition, but it might be better to just see what's happening. So let's take such a subgraph H. And what happens is that for any subgraph H prime of H, we have that the every degree of H is at most this happens. Why? If you just move this part and multiply it here, then inequality holds. Why? Because here, that's the pi value of H on the right-hand side, and the pi value of H prime on the left-hand side, and pi value of H was maximum. So this inequality holds. So you just divide it, and you get this. And furthermore, what do we know? This and this. So this is bigger. This is like roughly 1 over log times order of H. It is roughly 1 over log times order of H. And H prime is smaller than or equal to H. This number of vertices might be same or lower. Same, you just forget it. Lower, then this is bigger. So this is bigger, so this is almost average degree of H. So this holds. Also, we know that the minimum degree of H is at least half times the average degree of H. Indeed, if not, then we take a vertex P of degree more than half times the average degree. Then for H prime, which is H minus B, we can check that its average degree is bigger than the H. Contradiction 2. So this is staying with the thing that I said before. We just take the subgraph with height average degree, then this holds. Okay. And also we have to check that this has almost same average degree as G. What we know? We have that if a pi function on H is maximum, so it's at least the pi function of everything. So average degree of H is at least 1 plus gamma times H, 1 plus gamma times gamma of G, D of G. But what do we know? We just forget it, and then we just consider this. And then when the gamma become the largest, it becomes largest if the inside parameter is as small as possible. So this is 1 over log size, so it's a decreasing function. So when this is smallest, then that's what happened. But what happened? So this is at least 1 over 1 plus a gamma 1 dg. And how did we choose this? When this is 1, you actually choose the epsilon so small so that, let's say, you can check that this is small. Then what? This is at least 1 minus some constant times epsilon times dg. So this is almost same average degree as wanted. So lastly, we need to check expandant property. So let's say you consider X, which is the subset with the size at least K0/2 and at most half of the number of vertices in H. Then let Y be the external neighborhood of this. And let's say X prime is the remaining. And what you have? You have X, then Y, X prime. And there are no edges between here. And what? You take the average degree times X. And what we know is that it's all three set together covered all the vertices in H. So this is what? Average degree times the number of vertices in H minus X prime union Y. And if you multiply these two, then that's simply twice the number of edges. And you can write it this way. And what's the twice number of edges? Is like you count the edges here, count the edges here. That's upper bound. So 2 times the number of edges in X union Y, and 2 times the number of edges in Y union X prime minus TH and X prime union. But what do we know? This and this are like so let's say this is the subgraph. H prime of G. So DH prime is smaller than DH. So every degree of subgraph is no, sorry. This one. Always smaller than or equal to the average degree of H. So that means this is what? Average degree of H prime times the X prime union Y. So this is smaller than that. So subtracting factor is bigger. So this is almost 2 times the number of edges in X union Y. You can write it as again degree of H X union Y and X union Y. But what do we know now is that we know that for this graph, we know that this is subgraph of H. So you compute this pi function. This is almost 1 plus gamma of H times degree of H. So you just subtract it on here, then you get the inequality. So you just write it. And you divide it, and then you write it. So that's upper bound. So you have this. And then you divide both sides. Let's say you divide. Then you say, and then you divide on both sides, and you get what? X divided by side of X union Y is at most 1 plus gamma of H divided by 1 plus gamma of X union y. Okay, because x and y are disjoint, you flip it and you subtract 1, then you will get y divided by x if at least. You flip it and you subtract gamma of x union y minus gamma of h, 1 plus gamma of h. And we know that this is n most 1, so let's write half. So x plus y minus gamma of h. So what do we do? If first case, if x plus y has size bigger than 3/4 of everything, then as x has size almost half of h, we have y at least half times x as desired. So that's much better than what we want. Otherwise, if this one is smaller than 3/4 h, then you can bound it. So roughly, so what's this? This is like some constant times log of this is smaller than 3/4 h is like let's say this is size g, then this is like a log of 4/3 g. So this is lower bound one here. Because this is decreasing function, so this is smaller than h. So smaller one is fine. I mean, you get the bigger number and you subtract bigger number, then this is smaller. So this is at least this much. And from this, what you can see is that from this definition, you can actually check that the gamma x minus gamma c times x is at least like some expression times rho of x. Then using this, what we can get is that the y x is at least like some large number times rho of x, which is like desired. Yeah. So if epsilon is small enough, then epsilon is smaller than this, then that's like yeah, maybe I made the computation set up a bit weirdly. So instead of yeah, okay. So at least, I mean, maybe you have to change this rho as I mean, so epsilon is already inside of rho, and then maybe you have to pull it out and this as a, I mean, you have to write it, you might have to write the specific function, which does not depend on epsilon, and then epsilon press them all out here. But one thing what you know from this computation is that it is actually with changing some constant if necessary to this work. So that shows that its ratio is roughly some constant times lower. So you get the desired sublinear expander. Okay, so now we have collected these two theorem. And in next video, we will use this to prove the result by Encomlossi and Semoredi that the constant times t-square average degree guarantees a copy of subdivision of KT. Okay, thank you for listening. I will see you in next video then.